Here's a part 2 to the original discussion. My original intent was just to look through this physics book again and see if I could find anything worth talking about. There's a lot in here. And Hooke's law stuck out to me. I don't know if you can see that. It's on page 29 of this book. But basically, Hooke's law it had to do with tension and springs. He says, as the tension, so the force. And in Latin, it was written as ut tensio siccipes. I don't know if I pronounced that correctly. But if you remember from the previous talk I just gave, the compression during land formation on the interior of the brown dwarf is very high. So there also, you got to keep in mind, there are differences in the material coefficients, how much they can be compressed and how much they change given as much pressure is in those layers. Okay. Now, what happens is when the atmosphere dissipates, all those internal structures rebound because there was a lot of compression on those materials. So, as well, you have to keep in mind there are differences in material. Maybe some of those materials will rebound a lot more than others. So, say you would have like a thinner region right there. So they all rebound as the atmosphere dissipates and releases the pressure off the interior of the star. And then you have your contraction, because after all that material all the atmosphere is released, then the material will start contracting again, and you'll have this compression both in this direction and down, causing there to be very large folds. Now remember, given whatever material is in there will determine how the material folds, how much of it folds, and whatnot. And then you have, basic geology coming in, expressing if you have weathering, and then maybe this part's cut off, and then it shows like this weird jutting landmass that's out of place completely. But further, we have a spherical structure. Now, if you're going to have an entire object this big have all of its atmosphere dissipate, the compression will be from gravitation pulling it all towards the center. And if you have all that material moving towards the center, the top portions are going to compress. They're going to push against each other in this direction as well. Meaning, plate tectonics is doubly replaced because now you have a force that can actually push things against each other. The entire Earth is contracting because it's cooling. It's thermodynamic contraction, and depending on the coefficients of the material will determine how fast it contracts in certain places, and also can explain why there are certain areas where the material is still cooling and contracting, causing earthquakes. And this is about as far removed from cosmology as you can get when you explain mechanically how stuff happens, instead of relying on fairy dust and nonsense. Because what we have here is this material is made of real stuff here. It's nice granite, schist, sandstone, basalts, and you can look at these formations now in the light of the Earth being the center of an ancient star after it's had all its outer atmosphere dissipate away, releasing all of it and then contracting again over many, many millions and millions of years. As well, you have mechanical engineering. And remember, I was talking about reverse engineering the Earth. Well, yes, because if you can calculate the coefficients for those materials and how fast they would rebound and how much they would be compressed, you can literally determine how thick the Earth's atmosphere was at one point. And I guarantee you it was probably bigger than Jupiter. Well, of course it's bigger than Jupiter. It was as big as the sun. But you can calculate, given what material was where. Say this material was when the Earth was about the size of Jupiter, and this material was when the Earth was a little bit bigger than Jupiter, and this material formed when the Earth was about a little larger than a regular brown dwarf, which is, I think, Van Noyen's star, or I think that's a red dwarf, anyways. But you can calculate the materials based off of something in this regard. the stresses and strains of the material, the yield strength of the rocks, the ultimate strength. You can use Young's modulus, you can use Poisson's ratio, and there are different types of strength and stresses that I also want my readers to understand. The strength of material is very different for the material that you have, such as, if you can twist it, if you can compress it, if you can pull it, that's tensile strength. Compressive strength, I know concrete has a very high compressive strength. The impact strength, and that would be important because guess what? Earth has impacts. If you have a large asteroid hitting the Earth, then wherever it hits will determine how the material deforms and what kind of consequences does it have for the surrounding region. But of course, that can also be applied to a lot of the impacts that we see on Mercury, on the Moon, and you can determine what kind of material is there based off of how the impact happened. For instance, if you have iron meteorite strike a large ball which is completely comprised of iron, it's going to behave differently, and you're going to see evidence in the actual surface than if an iron meteorite were to hit a granite covered surface, or if it were to hit, say, a water covered surface and then it hits basalt, which then would have a different kind of impact. But anyways, there's a lot you can determine from this, and it's a much richer understanding than plate tectonics, which assumes the Earth was always solid and liquid material in its past. But we all know better. It was gaseous, very, very large, and at one point was completely ionized as a very hot young star similar to the sun. Okay, well, that's it. If you have any questions or comments, please leave them below. And make sure you read a lot of physics books. Like, if you see anything that sticks out to you, go ahead and speak up. Don't be afraid.